See, in our part 1 we derived the numerical differentiation formulas with 2 points x 0 and x 1. Now, in today's module, our part 2 of this module will derive first general numerical differentiation formula, also the expression for the error term using Lagrange's interpolating polynomial, and as a particular case of this general numerical differentiation formula, we will take n equal to 3. So, 3 tabular points x 0, x 1, x 2, and using this we will derive the formulas for those 3 points, which would be end point formulas and midpoint formulas. Also discuss error terms, and also these formulas will see that can be learned via Taylor series also. And in the case of numerical differentiation formulas, we will discuss about the round of errors today, that how the round of errors also play their role, and that is why this numerical differentiation formula is not regarded as a very stable method. And in that case, if reduction of the step size h is not yielding the desired accuracy because of round of errors playing more dominant role, what can be done in that case, what other alternatives are available for it, these all points we would be discussing in our today's module of part 2 of the numerical differentiation. So, now let us derive general numerical differentiation formulas using Lagrange's interpolating polynomial. So, let x 0 less than x 1 less than x 2 less than x n be n plus 1 distinct points, and we know that the f x is given by interpolating polynomial plus the error term, and p n x is the Lagrange's interpolating polynomial for our purpose. So, p n x, the expression we know is very well given by summation I equal to 0 to n L I x into f x I, where L I x are the Lagrange's coefficients, each of them is a polynomial of degree n, and we also know that L I x are given by the numerator in the L I x is given by product x minus x I, that is x minus x 0 into x minus x 1 up to x minus x n, and x minus x I term is missing. For example, if we take L 0 x, it is x minus x 1 into x minus x 2 into x minus x n. If we take L 1 x, it will be x minus x 0 into x minus x 2, x minus x 1 will be missing into up to x minus x n. So, numerator is the product of x minus x i's, but remember that if it is L 2 x, x minus x 2 is missing. So, it is product of x minus x j's, where x minus x I is not there, and denominator is a constant, which is nothing but in the numerator we have to substitute x minus x I. So, case of L 0 x, the numerator is x minus x 1 into x minus x 2 up to x minus x n, and in this numerator we will put x equal to x 0. So, x 0 minus x 1 into x 0 minus x 2 up to x 0 minus x n will be the denominator of L 0 x. So, these Lagrange's coefficients already we have learned in the chapter of interpolation. So, f x is given by p n x plus E x, where p n x is sigma L I x into f x I and plus the error term. Now, let us look at the error term. So, error term is given by product x minus x i's I equal to 0 to n. So, x minus x 0 into x minus x 1 up to x minus x n upon n plus 1 factorial and n plus 1 derivative at the point xi x. Now, this xi point is in the interval a b, but this xi depends upon the point x, and this xi x is not known to us. If we differentiate f x equal to p n x plus E x with respect to x, we get the equation f dash x is p n dash x plus E dash x. Differentiate p n dash x is sigma, it is a sum, derivative of sum is sum of the derivatives, f x I are constants. So, it is summation derivative of L I x, so L I dash x into f x I. Now, let us look at the derivative of E dash. E dash x is E is product of x minus x i's and f n plus 1. So, derivative of E is, let us apply the product rule, derivative of the product. So, 1 upon n plus 1 factorial, derivative of product x minus x i's, f n plus 1 as it is, and plus the second term, this product as it is and derivative of f n plus 1 xi. Now, second term is not known to us because xi is not known to us. So, this term is not known to us, we have no idea about d by dx of this term. But if x is one of the tabular point, then this product becomes 0, and then the error d e dash simplifies to only the first term, And so, let us put x equal to x j, because in that case the second term becomes 0. So, x is x j, where j can be 0, 1, 2, 3 n. So, x is any of the tabular points x 0, x 1, x 2, x n. So, E dash at the point x j is 1 upon n plus 1 factorial, this term, f n plus 1 derivative xi x j, and the product I equal to 0 to n. Here we get x j minus x I, and derivative of this product is I equal to 0 to n, I different from j, x j minus x I. And so, we can say that f dash x j is, put the term p n dash x, what we have derived, sigma L I dash at the point x j f x I, plus the derivative term 1 upon n plus 1 derivative f n plus 1 xi at the point x j, and pi I equal to 0 to n, I different from j, x j minus x I. So, now let us derive the particular case of this derivative, that is n equal to 2. So, we use this formula now for n equal to 2. So, first is, let us derive the polynomial p 2 dash. P 2 dash is sigma L I dash x f x I. So, let us write L 0, L 1 and L 2 and differentiate. So, L 0 x is, numerator is x minus x 1 into x minus x 2, as I explained to you, and denominator is put x equal to x 0 in this numerator. So, x 0 minus x 1 into x 0 minus x 1, and we will differentiate it. So, differentiation of x minus x 1 into x minus x 2 is, first put open it, it is x square minus x into x 1 plus x 2 plus x 1 x 2, denominator as it is, and if you differentiate this, denominator will be as it is, and numerator derivative of x square is 2x minus x 1 plus x 2 is constant, derivative of x is 1. So, minus 1 into x 1 plus x 2, this is 0. So, 2x minus in the bracket x 1 plus x 2, and denominator is a constant as it is, x 0 minus x 1 into x 0 minus x 2. And similarly, because see this is L 0 dash x and we know it is L 0, you getting x 1 x 2, x 0 minus x 1, x 0 minus x 2. We can say that L 1 dash x is 2x minus, now x 0 will not, x 1 will not be there. So, x 0 plus x 2, and denominator will be x 1 minus x 0 into x 1 minus x 2. In the case of L 2 dash x, denominator will be x minus x 0 into x minus x 1, put x equal to x 2. So, x 2 minus x 0 into x 2 minus x 1, and numerator will be 2x minus, in this bracket x 2 will not be there. So, x 0 plus x 1. So, these are the expressions for the L 0 dash x, L 1 dash x and L 2 dash x. And let us put x equal to x j. So, where j will be either 0, 1 or 2. So, p 2 dash x j is 2 x j, this is L 0 at x equal to x j. So, L 0 dash x j. So, L 0 dash x j is 2 x j minus x 1 plus x 2, denominator as it is, into f dash x, f x 0, plus second is L 1 dash at the point x j. So, 2 x j minus x 0 plus x 2 upon x 1 minus x 0, x 1 minus x 2 into f x 1, plus third term L 2 dash x j. So, 2 x j minus x 0 plus x 1, x 2 minus x 0, x 2 minus f x, x 2 minus x 1, f x 2. So, this is p 2 dash x j, and what is the error? E dash x j will be 1 upon 6 n plus 1 factorial, n is 2. So, 2 plus 1 3, 3 factorial 1 upon 6, n plus 1 derivative, f 3 derivative at the point xi j, and product I equal to 0 to 2 I different from j, x j minus x I. And so, this is the expression for the error term. Now, if we need derivative at, let us say, x 0, and let us assume the points are uniformly spaced with the uniform spacing h. So, let us denote x 1 as x 0 plus h, x 2 as x 0 plus 2 h. We are using j equal to 0. Similarly, we can use j equal to 1, j equal to 2 and so on. So, let us derive the formulas for derivative at the point 0. So, our estimate of derivative at the point x 0 will be given by the first sum of first 3 terms, that is p dash x 0, and error will be given by this term. So, f dash x 0 is, this is in the formula of L 0 dash x j, I am putting x equal to x 0, we get 2 x 0 minus x 1 plus x 2 upon denominator is the product x 0 minus x 1, x 0 minus x 2, f x 0, plus second term you will get 2 x 0 minus x 0 plus x 2, x 1 minus x 0 into x 1 minus x 2 f x 1, third term will be 2 x 0 minus x 0 plus x 1, x 2 minus x 0 into x 2 minus f x 1 f x 2, and error term 1 by 6 f3 at the point xi 0 we are calling it, and the product of xj minus xi is xi different from xj. So, x0 minus x1, x0 minus x1, x0 minus x1, x0 minus x2, and so it simplifies to f dash x0 is substitute x1 as x0 plus h and x2 as x0 plus 2h. So, this term x1 is x0 plus h, x2 is x0 plus 2h, x0 will cancel and we will be left with minus h minus 2h gives minus 3h, and x0 minus x1 is minus h, x0 minus x2 is minus 2h, product becomes 2h square. So, minus 3h upon 2h square fx0. Similarly, this term will be minus 2h by minus h square fx1, and this term will be minus h, x1 is x0 plus h, x0 cancels minus h by this is again 2h and h. So, 2h square fx2 and 1 by 3, 1 by 6 f3 is I0 minus h minus 2h. Here we can take 1 by h common, minus 3 by 2 fx0 plus 2 fx1 minus half fx2 plus h square by 3 f3 is I0. So, if we put j equal to 1, then our formula becomes f dash x1 is the middle term goes away, 1 upon h minus half fx0 plus half fx2 minus h square by 3 minus h square by 6 third derivative at the point xi1. And if we put j equal to 2, that is xj is equal to x2, then we get f dash at the point x2 is 1 by h half fx0 minus 2 fx1 plus 3 by 2 fx2 plus h square by 3 third derivative at the point xi2. So, here in this 3 point formulas, in the second degree fitting, error is of the order of h square, and in these formulas if we substitute x1 as x0 plus h and x2 as x0 plus 2h, then the on putting the we get these expressions, and in these expressions if I put 1 by 2 also I take common. So, it gets simplified to an elegant form given by f dash x0 is 1 by 2h minus 3 fx0 plus 4 fx0 plus h minus fx0 plus 2h, and error term is h square by 3 third derivative at the point xi0. And f dash the second formula, when j is 1, we put f dash x0 is that is 1 by 2h. See, what we are doing is these all three formulas, though this is x0, x0 plus h, x0 plus 2h, at any point x0 means we are changing x0 plus h to x0 here, we are changing x0 plus 2h to x0 here. So, this formula as it is. In the second formula, if I change x0 plus h to x0, this will become x0 minus h, this will become x0 plus h. In third formula, when I change x0 plus 2h to x0, this will become x0 minus 2h, this will become x0 minus h, and this will become x0. So, the third formula is f dash x0 is 1 by 2h fx0 minus 2h minus 4 fx0 minus h, and plus, because 1 by 2 we have taken common here. So, it becomes 4 and plus 3 fx0 plus h square by 3 third derivative at the point xi2. Now, if you look at the first and third formula, see here these first and third formula, they are called endpoint formulas, and the second formula is called midpoint formula. The reason is here the derivative which we are estimating at the point x0 is this is a midpoint, and the other 2 points are on the other 2 sides of the x0, x0 minus h, x0 and x0 plus h. These are the 3 points, and we are estimating derivative at x0. Whereas, in the case of first formula, x0 is in the beginning and x0 plus h and x0 plus 2h are the other 2 points in the forward sense, and in the case of third point, x0 is at the rightmost and the other 2 points are x0 minus h and x0 minus 2h. So, first and third formula are called endpoint formula, because you are estimating the value of derivative at the end point of these 3 tabular points, and whereas the second one is the midpoint, because you are estimating derivative at the middle point and the other 2 tabular points are on the either side of this point. There is one more thing, if you look at these error terms, the midpoint formula, the coefficient is h square by 6 half, whereas in the case of endpoint formula the coefficient is h square by 3. So, in the midpoint formula the error coefficient is half of the coefficient of the error term in the endpoint formulas, And moreover, in the case of midpoint formula, we need to evaluate the value of derivative only at the two endpoints x 0 minus h and x 0 plus h. Midterm coefficient has become 0. Though that we are evaluating the value of function at only 2 points, we are using only 2 function values, still it is called a 3-point formula, because we have used 3 points to calculate the, to estimate the derivative of the function at these points. So, this is the comparison between the endpoint and the midpoint formulas. Error of course is the same of the order of h square, coefficient is 1 by 3 in the error term, whereas in the midpoint coefficient is 1 by 6. So, it is half. Evaluation of function is at 3 points, where here it is only 2 points. So, midpoint formula more suitable as such in the error wise, and the endpoint formula will be more suitable when you want to estimate the error at the end point. When you need to estimate the error at the end point, at that time the endpoint formula is more suitable. Now, let us have a look graphically at this 3-point midpoint formula. So, you have 3 points x 0 minus h, x 0 and x 0 plus h, and let this be the graph y equal to f dash, slope of the tangent gives you f dash. Now, this is the point x 0 minus h, f x 0 minus h, this is the point x 0 plus h, f x 0 plus h. So, if you take the difference of these two function values, divide by 2h, this is nothing but the slope of line joining x 0 minus h, f x 0 minus h, and the line joining x 0 plus h, f x 0 plus h. So, midpoint formula is nothing but a straight line fit between the end points of the point x 0 f x 0, and derivative of this line is the estimate of the derivative of the function at the point x 0. So, computationally let us have a look. We have computed using a program the estimate of the derivative by applying this 3-point midpoint formula as well as 3-point endpoint formula using h equal to 0.5, h equal to 0.1 and h equal to 0.05. Let me make you one more point clear. See, though these are 3 formulas, first and third formula as such are not independent formulas. If in the first I change h to minus h, I will get the third formula. If I change h to minus h in the third formula, I will get the first formula, because your one of the points will be x 0, the other points will become x 0 plus h, x 0 plus 2h. So, as such these two formulas are not independent. So, if we look at the 3-point endpoint formula, h equal to 0.5, h equal to 0.1, h equal to 0.05, our approximate solutions are minus 0.405190, minus 0.327 and minus 0.321477. Exact we have seen it, errors are 0.084, 003 and 0007. So, as we are reducing the step size, errors are decreasing, relative error has come down from 26 to 0.95, less than 1%, if we reduce s to 0.1 and then 0.2339%. In the case of midpoint, see, both are 3-point formulas, but in the case of midpoint, as I said, no, error is half, estimated to be half of the error at in the case of endpoint formula, because here the coefficient is 1 by 3, here the coefficient is 1 by 6. If you look at the estimates are these, errors are now 0.036533, 0.001470, less than half of this and less than half of it here. Relative error 11.39%, 0.458257, 0.3339. So, here this midpoint formula, the relative error are percent relative error also less than half %, absolute error is also less than half of the absolute error in the case of endpoint formulas. So, midpoint formula is working better and with the less efforts, only 2-point function values we are using. So, as expected, truncation error u is order of h square. As we reduce h, our error term will go on decreasing. So, 0.5 we are making half of previous one, approximate solution is approaching near the exact value 0.320727. See, when we have become 0.003906, we have taken h, it is 0.320732 and 0.000977. The approximate solution has become almost the same, it is the same 0.320727, leading to absolute error 0. So, now similarly, as we have derived 3-point formula, these 3-point formulas can be also derived using Taylor series, and otherwise also. And similarly, we can also derive 5-point formulas and using either Taylor series or using Lagrange's interpolating polynomial. So, then the formulas which we obtain using 5 points are f dash x 0 is given by 1 upon 12 h f x 0 minus 2 h minus 8 f x 0 minus h plus 8 f x 0 plus h minus f x 0 plus 2 h plus h raised to 4, error is of the order of h raised to 4 by 30 f 5 xi lies between x 0 minus 2 h to x 0 plus 2 h. This is like your midpoint. The x 0 is in the middle, 2 points x 0 minus 2 h, x 0 minus h on the left side, and x 0 plus h and x 0 plus 2 h 2 points on the right side of x 0. And the end point formula is f dash x 0 is 1 upon 12 h minus 25 x 0 plus 48 f x 0 plus h minus 36 f x 0 plus 2 h plus 16 f x 0 plus 3 h minus 3 f x 0 plus 4 h plus h raised to 5 by 5 f fifth derivative, where xi is between x 0 and x 0 plus 4 h. Here coefficients are also large, and here you need evaluation at 4 points, here you need evaluation at 5 points. Error term is 1 by 30, here it is 1 by 5. So, this is also small. So, if you have tabular entries at near the both the sides of the point, then the midpoint formulas are more suitable. But if you are evaluating derivative at one of the end points of the table, then the end point formulas are to be used. Now, in the case of numerical differentiation formulas, truncation error we have seen. Now, let us come to round off errors. In the case of numerical differentiation formulas, round off errors also play an important role, for the simple reason the formulas involve the division by h. You have seen in 3-point formula, simple formula, 5-point formulas, all the expressions contain 1 by h, and when you are reducing h, to reduce the truncation error, we go on making h smaller and smaller. So, as we reduce the step size, it is amounting to division by small number, and as a result you very well know, because computers have finite precision, then round off errors occur. Moreover, numerator is also a difference of 2 terms which are very alike, f x plus h, f x plus 2 h, f x minus h. So, these are all h is small. So, these arguments are very near. So, it is also equivalent to taking sum or difference of 2 very almost equal numbers. So, the numerators also become small, denominators also become small. As a result, round off errors play quite important role in the case of numerical differentiation formulas. So, we can see if here, that is, see if your total error, if we calculate, estimate as truncation error in the case of 3-point formula, midpoint we are taking h square by 6 and f the third derivative bounded by m. So, h square by 6 m. And in case of round off error, see it is 1 by h is there, and let us say in the estimate of your summation of arguments of f at x 0 minus h and f x 0 plus h, absolute wise if the error is bounded by h by epsilon small number. So, round off error is of the order of 1 by h. So, result is, as we to reduce truncation error, we would like to make h smaller and smaller. As we make h smaller and smaller, truncation error will reduce in the order of h square. But the problem is, because it is 1 by h round off error will increase, start increasing as we make h smaller. This particular table I have taken from the book by Brady, and this illustrates the 3-point midpoint formula for a very simple function e raised to x and very simple argument x 0 equal to 0. Then as the step size is being reduced, 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 7, see the error as such is going on decreasing up to 10 raised to minus 6. Up to 10 raised to minus 5, but then further reduction in the step size is increasing the error, total error is increasing, and the reason is the total error is started increasing because round off error has started increasing as you reduce h because of finite precision of arithmetic in the digital computers. And so, in the case of numerical differentiation, beyond a particular h optimal size we cannot go. And this is the graph which illustrates this phenomena. See, this is your graph y equal to 1 by x similar h, that is epsilon by h type. It is a hyperbola and As you increase h, this is decreasing, but as you decrease the step size, round of error is increasing. Whereas truncation error is parabola y equal to x square type, order of h square 1 by 6 m into h square, and so the truncation error increases as you increase h. So, truncation error reduces if you decrease h, and so there is this is the optimal h total, because this is the graph which is plotted of total of this value and this value, total of this value and this value, total of this and this. So, as you reduce h slowly and slowly, this is the optimal point, beyond which if you will increase, then the total error will start increasing. There is no point of reducing step size beyond a particular optimal point. Up to this, total error is decreasing, but then if you reduce below than this, then the total error will start increasing again because of round of errors. And so, in the case of numerical differentiation, we have to be very careful, that is the process becomes unstable even if the no inherent errors are there in the data, because beyond a certain limit we cannot achieve the accuracy, because we cannot make h further smaller and smaller. So, beyond the optimum size of h, we cannot reduce h further, and round of start errors will start dominating beyond the certain limit of h. And so, what are the alternatives? So, alternatives are, that is, you approximate function in the case you need more accuracy and the round of errors have started dominating over the truncation error. In that case, instead of using interpolating polynomial and its derivatives, you approximate function f by some other method, that is maybe least square curve technique you may use, and fit a lower degree polynomial using least square curve fitting, and then differentiate that polynomial. An estimate of the derivative of that least square curve polynomial at the point can be taken as the estimate for the derivative of the function. Or the other alternative can be, instead of fitting least square, you can also think of fitting a cubic spline, use cubic spline interpolation to the data points as the case may be, and again differentiate that cubic spline interpolating polynomial, and derivative estimate of the derivative of that polynomial, the cubic spline polynomial, can be taken as the estimate of the derivative of the function. About the numerical differentiation process. So, in sum, in short, what we have learned today is that we approximate function by interpolating polynomial, and the formulas we have derived for special case n equal to 1 and n equal to 2, and also I showed you the formulas for n equal to 4, that is 2-point formula, 3-point formula and 5-point formulas can be used. If the points are uniformly spaced, we can use midpoint formula if we know the point on the values of the function on the either side, or we use n-point formula if we know the values on one side of the points, and we can use numerical differentiation formulas to arrive at the estimate of the derivative of the function. At the same time, we have to be careful here, because in the case of numerical differentiation formulas, round of errors start playing important role. So, if we go beyond the optimal value of h, if we try to make further smaller h and we want still we need more accuracy, it may happen that the solutions may start becoming unstable, errors may start increasing, and in that case, if we still need further accuracy, one may use a least square curve fitting or a cubic spline interpolation polynomial. So, thank you for listening and thank you for visiting EPG Pathshala. In our next module, we are going to learn about numerical integration, that is integral of a function, and you will see that numerical integration is a highly stable process as compared to the unstable process of numerical differentiation. Thank you once again.